The ESB, in cooperation with the European Community, launch a major research project to find a more economical and efficient use of energy in the home. The project involves building 6 houses. A standard house designed and built to current specifications. Group B, C, and D, designed to have 20% less heat loss, and Group E and F, designed to have 50% less heat loss. From the start of the project, design discussion meetings between the project architect, the service engineers, and the builder ensure that all facets of the design are integrated: architectural, building services, and construction. The planning stage is complete, it's over to the builder, and foundations and blockwork see the project underway. The site at Kilcock, County Kildare, forms part of a housing estate which is in the early stages of development. The type of house already built is typical of many contemporary housing developments in Ireland. The 6 houses in this research project are built with standard indigenous materials, using conventional building techniques employed by builders in Ireland every day. They look no different from the house next door, but the design is different. Special trenches are provided throughout to carry cables for monitoring purposes. External wall insulation is a proven success in energy saving, and here in one of the houses, a 40mm thick sheet of polystyrene is placed in the 100mm cavity. The sheets are held to the inner leaf by wall ties. The insulation in House A complies with current building regulations: solid concrete floor with 25mm insulation, cavity walls with 40mm insulation, standard roof with 100mm mineral fiber between the joists. A 100mm section of insulation is placed in the wall cavity of one of the houses. It fills the cavity fully and the blockwork is built up around it. In this group, the insulation is considerably improved on the standard house. The floor has 40mm of insulation, the cavity wall has 100mm, there's an additional 50mm of insulation in the attic, and double glazing was used throughout. Despite the many additional features of the architectural design, progress is maintained at a steady pace. This type of insulation, called dry therm, can be used as full cavity insulation. A technique of vertical layering of the fiber during manufacture is designed to ensure that moisture drains down through the insulation under gravity and so prevents it seeping through the inner leaf of the wall. As the ceiling beams are erected, the houses look indistinguishable from any other new Irish home. In this unfinished state, they show how important it is to keep the heat in and how it can be so easily lost. The only energy source, apart from nature, in this whole project will be electricity. And that will be used efficiently by skillful and planned use of insulation and by the use of automatic controls and modern electric heating systems. The roof tiles complete the outside shell. These are standard interlocking concrete roof tiles laid on tiling battens over felt on braced roof trusses. Plasterers complete the external rendering of the blockwork. The walls were constructed with 2 leaves of 100mm solid block with a 100mm cavity between the leaves. At one of the many meetings of the project team, the architect discusses the function of a plastic air duct. In highly insulated houses, condensation can occur in the attic due to lower temperatures and lack of adequate ventilation. The use of these air ducts ensures that the insulation does not completely fill the gap between the roof tiles and the angled ceiling and wall plate, thus allowing enough air in under the eaves to ventilate the attic space and prevent condensation occurring. At this stage, the electrical services are installed. Heat recovery units are used in the advanced design houses E and F. They are installed to recover heat which would otherwise be lost. This heat recovery unit draws in fresh air from outside by fan, and heat is recovered by passing the warm used air over the cold incoming fresh air in a heat exchanger. The fan speed can be varied according to requirements, and the used air is then expelled through ducts in the roof space to the outside. With this unit, it is very important that the external doors and windows are well sealed to reduce natural infiltration of air. Also in houses E and F, heat distribution on the ground floor is achieved by installing coils of polypropylene pipe in the floor screed, above the floor insulation. This system provides a uniform temperature distribution in the room. Upstairs, pipes are laid to conventional radiators, which are used to distribute heat to bedrooms and bathroom. Here, indirect solar panel systems with separate solar water store are used in conjunction with the electric immersion system in houses B and F. The systems used are similar to ones already tested and found to be satisfactory by the ESB. In the early planning stages, the design team were conscious of southern orientation with the use of solar panels in mind, and of course better general exposure to the sun. The solar panels are used to preheat the domestic hot water requirements. Water is pumped through the glazed copper panels which absorb heat from the sun's rays. This heat is transferred to the water in a storage tank. An electric immersion unit heats it further to the desired temperature. The space between the door frames and the blockwork is sealed to prevent air infiltration to the house, and also behind the insulation in the cavity wall. A feature of the architectural design is the provision of double doors at the front and back of the houses to reduce heat loss through air changes. Sticky bead insulation is used in houses B, E and F. This differs from the other forms of insulation used in that it is injected into the wall cavity after completion of the walls. This minimizes the effect of insulation on the construction schedule. The beads stick together after injection to form a solid block of insulation which prevents penetration of moisture. 3 of the houses, B, C and E, have heat pumps installed in the back gardens. But what is a heat pump? It works rather like a fridge in reverse, by extracting heat from the outside air and then using this heat to heat your house. The heart of the heat pump is the compressor. Here we see the low temperature heat exchanger and the high temperature heat exchanger. The fan draws air through the heat exchanger and heat is extracted from the air. The refrigerant circulates continuously in a closed circuit, taking heat in the low temperature exchanger and giving heat out in the high temperature exchanger. The hot refrigerant heats the water, which is then pumped out to the radiators and back again to the heat exchanger. Here we see how the hot water from the heat pump outside circulates through the radiators and heats the house. During this whole project, Irish manufacturers were used where possible. Here in the General Steel Factory in Carrickmacross, County Monaghan, heat pumps and Centrelec systems are made. Centrelec is an electrical central heating system developed by the ESB. It uses cheap nitrate electricity to maintain a central water store at 90 degrees Celsius. This hot water is circulated to underfloor coils and room radiators to maintain the rooms at preset temperatures. The Centrelec water store fits neatly in the upstairs landing, behind sliding doors. Any heat given up by the water store is maintained within the house, unlike an external boiler where the heat given off is totally wasted. In any energy-efficient system, accurate and sensitive controls are a feature throughout. The houses now near completion. Attention shifts to the external fittings. This machine, reflecting the modernization of Irish building techniques, is used on-site to press out the gutters to measure from sheet aluminium. The levels of glazing vary from single to triple in this project, enabling comparisons to be made based on recorded heat losses. The amount of heat loss in a building is very dependent on the type of glazing used and the area of glazing relative to the total wall area. Typically, as much heat is lost through the windows as through the wall area. Just as the windows lose heat to nature, the solar panels absorb heat from nature. The houses are offset from each other to increase the area of wall directly exposed to the sun. All the houses have attic insulation. It is the easiest of all insulations to install and one of the most cost-effective ways of reducing heat loss. The thickness of attic insulation varies from 100 millimeters in the standard house A to 200 millimeters in the houses of advanced design E and F. The increased insulation in houses E and F further reduces the heat loss. The floor has 50 millimeter insulation, the cavity wall has 100 millimeter, and there's 200 millimeters in the attic, and triple glazing is used throughout. In one house, a mix of conventional electric heating is used. Storage heaters on the ground floor provide the basic heat, with temperatures being topped up as required by convector heaters. Convectors are also used in the bedrooms, with timers to control the hours of use. But is it all going to work? The ESB has installed an extensive monitoring system which records information from more than 500 different points. Over 1 mile of cable is used in each house, and these transducers are all the occupants will see. The weather station, where 5 different weather parameters are checked and recorded every 10 minutes. A central computer and ancillary equipment are installed on site. The results can be checked on the spot and changes made in the pattern of recording. Graphs can be produced on the variations in temperature in individual rooms over a period. The data is stored on a data cartridge. The computer on site is connected by phone line to ESB headquarters in Dublin, where daily observations are made. A data cartridge containing over 1 week's recorded information from the 500 monitoring points in the 6 houses and weather station is put into the computer in headquarters. Here the data is checked and analysed on the ESB's main computer system. The results show clearly that the higher levels of insulation and glazing, the draft ceiling and double doors, and the conservatories have contributed to a substantial reduction in energy requirements. The houses will now be occupied and tested in more practical conditions. In this research project, 4 different heating systems are being monitored. Solar panels in houses B and F provide domestic hot water. Heat pumps in houses B and E provide space heating and domestic hot water. The ESB Centralex system is installed in houses A, C and F for space heating. Night storage and direct heating in house D for space heating, while domestic hot water is provided by an immersion heater. And house C uses a heat pump for domestic hot water only. This is one of our houses for tomorrow, and in terms of energy consumption, it is where all families of today would like to live. Now the houses and the computer are chatting to each other with measurements coming from 500 points about temperature, heat flow, solar radiation and electrical energy. The results of this project, when fully analysed, will make a significant contribution to the design and building of Irish houses in the near future.